So our first question, it's asking, as we change the radius of a wire, how does the current change? So we're given our vertical axis and our horizontal axis. So we're asked first, is the current density uniform? So current density can be seen as, this is current over area. So this is our y-axis over our x. And we know when we have our change in y-axis over our change in our x, this is equal to our slope, right? So it's asking if our slope is consistent. So looking at this graph model, we have a linear graph model. So in that case, is it uniform? Yes. Okay, so now it wants us to find what the magnitude of our current density is. So we will use, okay, so now it wants us to find our current density at this point here. So this is, our current is equal to, so if we look at this graph, this is 4 milliamps. And so that's 1, 2, 3, 4, 5 of those. So each one is equal to 1 milliamp. So this is going to be 5 milliamps, right? Hold on. Yeah, it actually just wants our, oh goodness, it just wants our slope. So we can do our change in y. So let's use this point here. So this is I, so that's 4 milliamps. And that's over. So if this is 4.7 right here, so if we take 3/4 of that, we'll be in line. So this is 3/4 of our 4.7 times 10 to the negative 6 meters squared. And this is times our pi. This will give us a current density of 4 times 10 times to the negative 3 divided by 0.75 times 4.7 times 10 to the negative 6 times pi. And this gives us our answer of 361.202. And so it's not quite on the mark, but it is definitely close. And this is 2 amps over meters squared. Okay. In our next question, we are asked to solve the current in the wire, the magnitude of the current density, and calculate resistivity of the material. So if we start with A, so we're given the length of our wire, the diameter, the potential difference, and our resistance. So using Ohm's law, IR, we're going to find for current. So this is equal to I equals V over R. And we can plug in our values we already know. So we have 24.3 volts, and we have 13.8 milliohms times 10 to the negative 3. And this is 24.3 divided by 13.8 times 10 to the negative 3. And this gives us 1,760.87 amps. So that is our first question done. Our next question asks for our current density. Current density is equal to our current over our area. So we have our current, which we just solved. And we have the area. So this is pi r squared. And our r in this case would be equal to 7.36 divided by 2. So this is 3.68 millimeters. Or this would be equal to 0.00368 meters. So we plug that value for our radius in for r. This is 0.00368 squared. This is equal to 0.87 divided by, so pi times 0.00368 squared. And this is equal to 4.138 times 10 to the 7 amps per meter squared. Lastly, for part C, we want to calculate the resistivity of the material which the wire is made out of. So we see that our units are ohms times meters. So in that case, you can think of this as r times our length. Sorry, actually we'll need the volume. So this is going to be A over L. Okay, so we have our value for resistance times 10 to the negative 3. Our area, which was pi times 0.00368 squared. And this is over 5.51 meters. And this is equal to 13.8 times 10 to the negative 3 times pi times 0.00368 squared. And it's divided by 5.51. And this gives us 1.065 times 10 to the negative 7 ohm meters for resistivity. Okay, in our next question, we are given a circuit that's connected to a 6-volt battery and takes 3 cross sections of areas but have different conductivities. So given the electric potential function V as a function of x along position x and strip, the horizontal scale is set to xs is equal to 9.12 millimeters. And section 3 has a conductivity of 3.021 times 10 to the 7. So what's the conductivity of section A, 1, and section B, 2? All right, so this one is already accounted for. Okay, so key detail that I would note is that they have the same cross-sectional areas. So that means they have the same current density because the same current is flowing through it. Right, so that means the current density of 1 is equal to the current density of 2 equal to current density of 3. Okay, so how this will work. So what we're going to do for this one, since we know that all of our j's are equal, I'm going to use this equation to model our statement. Actually, wait, let me write this out. This time over A. This is equal to our conductivity times our electric field. And our conductivity times our electric field 3, where our electric field is equal to our change in our voltage over our change in our distance, so our change in our x. So that's what we're going to use here. So we're going to use E as the slope for each of our sections. So if I start with section 1 is equal to, so we have, okay, so J1 is equal to conductivity value 1, and this is, so we have our scale set by 9.12, and we have 11.16 volts to start. So we're starting at 11.16, and we're going down to, so this is 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 sections. So we're going down to 7/9 now of 11.16. 7/9, and this is minus 8.68. So that's our change in voltage and our change in our distance. So this is at half of 9.12. So this is negative 4.56 times 10 to the negative 3, because we're in millimeters. And this gives us and this is times, so 11.16 minus 8.68 divided by negative 4.56 times 10 to the negative 3. And this is hold on. This is 543.859. Okay, so that is our first slope. Our second slope for section 2. So now we're going from 8.68 volts and our change is, so this is down to 3/9. So 3/9 of 11.16. And this is minus 3.72. Oh, sorry, this is meant to be negative, because this is a negative slope. And this is from 4.56. And this is down, this goes down too. So let's find what 5 out of 8 is. So 5 out of 8 times 9.12 would give that section there. Is equal to, this is 8.68 minus 3.72 divided by 4.56 minus 5.7, and this is negative, or, oh yeah, sorry, times 10 to the negative 3. And this is 4,350.877. Okay, and we can already find what J3 is going to be because we have our value for conductivity here, which is 3.021 times 10 to the 7. And then we just need to find what this last slope here is. So this is from 3.72 down to 0. And this is from 5.7 down to 9.12. Okay, so this is 3.72. That's divided by 5.7 minus 9.12. And this is times 10 to the 3, the bottom. So this is going to be, negative 3. Sorry, let me explain this really quick. So I put 10 to the 3 because this is how we convert to our meters. 10 to the negative 3 at the bottom. So if we flip this, it becomes 10 to the 3 at the top. And this is going to be, so times 3.021 times 10 to the 7. And this is this enormous number of 3.286 times 10 to the power of 10. Okay, so we're going to sub this value in for J1 and J2 to find our conductivity values, because we said all of our J's are even, because our surface area was the same. So we're going to take this value and we're going to divide it by, so let's start with our red one first. So this is negative 4350.877. Okay, and this is going to give 7.552 times 10 to the 6. Sorry, this is meant to be negative, so then that will give us a positive conductivity value. This is our first answer. And plugging this in for our J1 and isolating for our first conductivity, we're going to take negative 3.286 times 10 to the 10. We're going to divide it by negative 543.859. And this is going to give 6.042 times 10 to the 7. And our units are in ohms, meters, 1 over ohm meters. Okay, so that is our third question down. In our third question, we have two circuits with a charged capacitor that is to be discharged through a resistor when the switch is closed. In figure A, we are given our resistance and capacitance values, and we are given the resistance and capacitance for the second circuit as well. So this is an RC circuit, so we're going to use this equation Q equals Q naught times E to the power of negative T over RC. And we know that tau is equal to RC, right? So we can rewrite this in our form. So negative T over tau. And we want to find time, so we have to isolate for our T. So we are going to apply ln. I'm going to move this Q over. So this is our Q over Q naught. And this is equal to negative T over tau. So now I'm going to solve for the first and second taus for our circuit. So in our first one, we are given tau as, so we're going to use our resistance. So that's 20.7 ohms times 5.28 times 10 to the negative 6 farads. So this is 20.7 times 5.28 times 10 to the negative 6. And this is 1.0826 times 10 to the negative 4. And our second value for tau, I'm going to write in blue, is equal to 11.1 ohms times 8.33 times 10 to the negative 6 farads. So this is 11.1 times 10 to the, times 8.33 times 10 to the negative 6. And this is 9.2463 times 10 to the negative 5. Sorry, I didn't quite finish isolating for t. So then, if we isolated for t, this looks like our charge ratio. And this is over 1 over tau 2 minus 1 over tau 1. Okay, so this is the equation that we're going to use. So let's go forward with that. So then we want our time. So this is our ln of our ratio, which is given 1.65. And this is over 1 over our taus, which we found. So we're going to start with 9.24 times 10 to the negative 5. And this is over 1.0826 times 10 to the negative 4. And this is equal to, this is ln times 1.65 divided by, so 1 divided by 9.2463 times 10 to the negative 5, and then minus 1 divided by 1.0826 times 10 to the negative 4. And this gives 3.17 times 10 to the negative 4 seconds. If we want milliseconds, that is 0.3173 to 4 milliseconds. So it's not quite what we got in our answer, but it is relatively close. So that is that question done. Okay, so our last question deals with an RC circuit as well. I'm going to let you try this one on your own. So I'll leave this on screen for you guys to try. Let me know how it goes. And if you guys need a solution, I can do one up for sure. But I'd like you guys to try this one on your own. And the answer is there. So feel free to try that one for yourself. That takes us to the end of this video where we covered some practice questions for RC circuits as well as Ohm's law, resistors, and resistivity. I hope you guys enjoyed. I hope you found this helpful. And yeah, let me know if there's anything I need to change or if there's anything I missed. And yeah, I will see you in the next one.